What were we talking about last time? Yeah, eigenfunctions and eigenvalues. And can you give me like a generic eigenfunction, or do you have an example of an eigenfunction? Or any we talked about in the past or might become really, really important in the future? H bar, what else do I need with this thing? Yeah, wave function is fine. And then what are we going to get out? Yeah. In this case, it's E for K, and then times what? Yeah. So how do you know if something's an eigenfunction? You got to get that same function back out after you operate on it. Okay. You said wave function hesitantly because we really haven't talked much about wave functions, right? I mentioned them a little bit, and then we just kind of moved on. Today, we're going to spend time talking about what a wave function is, the rules you need for a wave function. We're going to also talk a little bit more about operators, something called Hermitian operators. Like somebody last time asked me if you have, I don't know, like operator O, like does the complex conjugate have to go first, doesn't it? When does it? Like there are answers to that. The strict answer is it depends. In most of our cases, it won't depend. But we have to try and prove that. Then what we're going to do is take all this mathematical junk that we're learning and we're going to apply it to a simple one-dimensional system. Actually, we're going to find a lot of information, chemical information out from this one-dimensional system. Then we'll move to 2D and 3D, and we're going to spend a lot of time in the 3D realm. Dr. Ogawa, did you guys talk about radial functions and spherical functions? No? Okay, that's fine. I'm thinking he's waiting until we cover it here before we can talk about it there. Okay, so big point. We're going to talk about wave functions. What do you guys know about wave functions? And if nothing is the answer, that's completely okay. So you can give me any type of information to work with about a wave function. Yeah. There's a bunch of stuff we talked about in lab relating to it. Why do we care about the wave function? What does it model or describe? Yeah, it will involve potential and kinetic energy, but what are we trying to model? Like what particle? Yeah, electrons. You can look at nuclei that way too, but we use the Born-Oppenheimer approximation and get around having to worry about nuclei, really. So really what we're looking at is a mathematical function to describe the wave-like behavior of an electron. That's the formal definition of a wave function. So it's purely mathematical. Function to describe wave-like behavior. I'm going to use a particle. But really, we care about electrons. The mathematical part we're going to hit in a second, but you can't measure a wave function. It is impossible. What symbol do we give for wave functions? Yeah, the trident, psi. I have a friend who works for Intel, and Tom, if you're watching this, he has that tattooed on his body. I can't imagine being that big of a nerd to ever have that happen, but I think it is a cool looking symbol. Okay, there are some rules that wave functions have to follow. The very first one, and this is based off of Born's interpretation, so Max Born, how he interpreted it, but the very first one is they have no physical significance. Might be going, why the hell are we talking about it? But that is the very first thing. Well, no direct, physical significance. Meaning we can't measure it. The second rule is it must be a continuous function. I know it's been a while since some of you have taken calculus. What do I mean by continuous? Yeah, it doesn't have any asymptotes or breaks anywhere. So if I plot like a sine or a cosine function, is that continuous? Yes. What would be a good trig example that is not continuous? Yeah, a tan function. It might do whoop. Oops. But at this point, there's a break. Feel like you remember that? Okay. It must have a continuous slope. And I think that's one of the requirements in order to be a continuous function. It must be single valued. Do you get what I mean by that one? Okay. So let's say I have some function f of x is equal to x minus 1. So if I have f of 2, what's my value going to be? 2 minus 1, 1. Now let's say I have another function, g of x, and that's equal to x squared minus 1. Okay. If I plug that in, there's a couple different solutions to this one, right? What are my possibilities there? Yeah. And both are correct, right? This would be an example of something that is not single valued, or this would be a single valued function. Does that make sense? Yeah. Yep. There's other crazy functions out there too that you can think of that have multiple answers. So the other thing is it must not be infinite over a non-infinitesimal range. So no matter how closely you zoom in on that function, you're not going to suddenly see a spike to infinity. So it can't have an infinite value. Must not be infinite over a finite region, or a non-finite region. Infinitesimal. Except we'll try that again. Trying to write infinitesimal down there. Okay. After that very first dot, I saw everybody snicker. Why did you think that was funny? So what were you thinking when we wrote that one down? Yeah. The whole point of what we're doing is to measure something, right? So if we have this thing that you can't measure, why the hell are we talking about it? So, question. If wave functions have no direct physical significance, why bother at all? Because we can't measure it, right? So what the hell? If you take the wave function times its complex conjugate, you can actually get a probability distribution. You get the electron density distribution. That's why we care about it is it can lead to something interpretable, something physical. The other thing is you can use operators and you can get different values out. Like, for example, shielding constants for NMR. You can calculate that if you know the wave function. So based upon the Born interpretation, or a one-dimensional system, we're going to write down some words. You necessarily don't have to write down these words, but this is where that interpretation comes from. If the wave function of a particle has a value psi at some point x, then the probability between determining of finding that particle between x and x plus dx, so we're changing x just a little bit, is proportional psi squared dx. You've probably had psi squared dx called something else. Oops, psi squared. This is the probability density. What do I mean by probability density? Because you guys have heard about probability density of electrons around an atom, right? So what does that mean? Yeah. Probability density, likelihood. Oops, because I'm spelling likelihood wrong. Probability of finding an electron. So if you're looking at this and you want to know the probability of finding that point, we utilize the following equation. And in most cases, you can have it flow to this. Okay, what do these symbols mean? Yep, wave function. All right. Other stuff. Yep. This P is a probability. Other stuff. What's the star again? Yep, complex conjugate. And what about that d tau? It can be. It's whatever coordinates you're considering. In most of our cases, we're going to say our systems are time independent. So we would have X, Y, and Z. But time does change stuff. The coordinates of interest. Okay, so let's look at an example. Am I okay to erase this stuff? Okay. Sample for an electron having a 1D wave function the range 0 to 1. What is the probability finding the electron in the first half of the range? All right, what are we looking for? Specifically? Yep. Okay. What information is important to us? Wave function, definitely. What's something else that's important, Will? Yeah, the range. Do you know what that statement means, or not really? What it means is the wave function is valid over that range of 0 to 1. If you try to operate outside of that, all bets are off. It might not describe the system properly. Lily, can you tell me something else that's important? Yep. Because what does that mean for our tau? It's not d tau, but d, yeah. And one more important thing that we already kind of said we need to find. What region are we looking at? Yeah. Okay. So we're looking for a probability. We have to follow this sort of format. Am I okay to use yellow here? I feel like using yellow. Okay. What are my integration limits? Yep. 0.5. We have psi star, psi. What else do I need here? Yep. Okay. Psi star, the complex conjugate. If I take the complex conjugate of this wave function, does anything change? See a couple head shakes. No, why not? Yeah, no why. Don't have to worry about it. I love functions without any I in it. It's just the same thing. So again, square root of 2 sine pi x. And what do I got to multiply that by? Yeah. Okay. Want to simplify that for me? Let's move that up here. Still have our integral. What's going to happen with the stuff in between? What do we get? Yep. Okay, how many people know how to do that right now? I don't. What would you do? Yeah, you could take out the 2. All right, we'll do that. 2 goes out front. Actually, do I want to do that? Yeah, I'll do that. Oh, God, I don't even know. That's probably how you solve it, if you wanted to solve it mathematically. You want to know what I do? I toss it in Mathematica. I look up a table of integrals. I check the 2 results. On your Quizlets, you look, there's a last page of possibly misleading information. Is there any possibly misleading information that we could utilize to help us out? Find one. Integral of sine squared bx is the one that we want to utilize. Oh, what am I forgetting? Yeah, shame. What's b in our case? Yep, pi. So if you look this up in the table of integrals, what you will find is x divided by 2 minus 1 over 4b sine 2bx. We're going to use that to solve our integral. It's nice and easy. You just have to plug and chug. Did I ever talk to you guys about these big tables of integrals or things, or historically about tables of integrals, or never? Okay. If you look, do you know what nationality most people, like if you look in the big one in the math area, what nationality most of the people are who solve those things? Yeah, they're Russian, because their options were to either go to war or do calculus. And a lot of them picked to do calculus. Well, some of them, not a lot of them. Okay. Let's do our integration. We're going to get 2. We get x divided by 2 minus what? Yep. Times what? Yep. And what are my integration limits? Yep. So now let's plug that stuff in. Does that look okay? Nope. What should I change? Plus sign here. Big cross. Look okay now? All right. We can simplify a lot of this junk. Sine of 0 is what? Yep. So what happens to this? Yep. 0. Don't have to worry about this part. All right, 2 times 0.5. Yep. Sine of pi. Yep. That's 0. So we're left over just with this. What's the value of it then? It's 0.5. Okay. We have a result. What does 0.5 mean, though? Yep. You have a 50% chance of finding the electron. What would be the probability if I extended it over the entire range? 100%? Or mathematically, what would it integrate to? It'd be 1. What if I took the first half of the box, and then I wanted to know the second half of the box, and I added them up, what would it be? Yeah, it'd still be 1. So even though there's a lot of weird, kooky quantum stuff going on here, check reality a little bit. There has to be the probability of finding the electron somewhere in your range. Does that make sense? You have any questions about wave functions? All right, let's keep moving on.